Hello and welcome to the Daily Space for Wednesday, July 11th, 2018. I am your host, Dr. Andres Plazas, and we're going to bring you a roundup of today's news from space and astronomy. So, we're going to start with some brief news from TESS, the Transiting Exoplanet Survey Satellite. And these are very short news, but the test team has reported that the spacecraft and the cameras are in good health and that the spacecraft has successfully reached its final science orbit. They are doing some tests in order to optimize spacecraft performance and with the goal of beginning science at the end of July. So let's remember that TESS was launched on April 18 on one of the SpaceX Falcon 9 rockets. And this is a mission that will find exoplanets using the transit method, and they will survey about 200,000 of the brightest stars that are near the sun. And we're hoping to find a few hundreds to be in the range of the Earth-sized and super Earth-sized exoplanets. So yes, we want to find planets that look like our own. So this brief report is telling us that the mission is going through commissioning. Every time you try a new instrument, of course, you need to have a period of testing and adjustment before you start science operations. And this is a period, of course, that serves to test how the spacecraft and the instruments are performing and then determines if you need to do any changes before the proper mission starts. And it seems that everything is good so far, although this seems to indicate that they're a little bit behind schedule, although it's alright. It's a complicated space mission, and it's good to do tests and make sure everything is okay instead of rushing things up. So yeah, that was that with respect to test. Very short news regarding that, but now that we're talking about commissioning and science verification, I have another story that is also about testing a near an infrared instrument, and this time imaging a galaxy cluster, a star cluster, I'm sorry. So let me actually go back to the actual image of the galaxy cluster. Um, yes, now you guys should be able to see the galaxy cluster. The star cluster is not a galaxy cluster, it's a star cluster. Sorry for that. So again, I was saying this is an image of a star cluster called RCW38. It was captured by an instrument called the HawK-1 infrared instrument mounted on the Very Large Telescope in Chile as part of the European Southern Observatory. And this is an image that was captured as a part of tests of observations in a process known as science verification. So you, as I was saying, like with tests, you go through something called commissioning, where you do a lot of engineering tests, and then after that you start taking images that mm, are images as if you were actually doing your science mission. So this is called the science verification period. This is for, as I said, for the infrared instrument called HawK, but it's also testing a system called GRAL, like GRAAL, which is a system of adaptive optics. So the cool thing about this is that by looking into the infrared wavelengths of the of the in the sky, this instrument HawK can examine this dust shrouded star cluster, and then you can actually see the star formation that is going on between the inside the cluster. And this is a cluster that contains hundreds of young and hot massive stars. It is about 5,500 light years away in a constellation of Vela or the Sails. And the central area in this cluster is visible as a bright blue region, as you can see, and it is inhabited by numerous very young stars and protostars that are still in the process of forming. So this image is we can contrast this image with what you can actually see in the optical. So this is the novelty about this instrument. We're using near infrared wavelengths that actually are able to go through the dust and let us see what's going on behind. Because if we compare the image of this cluster with previous instruments that have taken images in the optical, which is what we can see in on your screens, you can see that there are fewer images. Now, these images in the optical appear empty of stars due to the dust that is actually blocking our view of the cluster. But the good thing about using this near infrared instrument is that we can go beyond what the optical wavelengths are telling us. And I also wanted to show a picture of the actual instrument. In the past, I have worked a lot with instrumentations, with the charge coupled devices and infrared detectors doing weak gravitational lensing. So I like to see how these instruments that are look very complex and very delicate and very pretty cool, because an instrument is basically a way of extend our senses. In a way, we have a certain limitation with our own senses as human beings, but then we can build these cool instruments that actually allows us to see what we usually don't see. So anyhow, this is a picture of this the Hawk instrument. And I mentioned before that they were also testing the adaptive optics system. So as you may or may not know, so in adaptive optics, so usually what we have is these sophisticated little chunks of mirrors that can change their shape. They're deformable mirrors. And why do we do that? Because of course, when you have a telescope on the ground and then you're looking through the atmosphere, you're looking at the image of a celestial object through the atmosphere, then the atmosphere is gonna distort the images of the sky, of course. So engineers and scientists throughout the years have come up with a way of actually measuring the distortion of the atmosphere. If you have, for example, you're looking at a celestial object and next to it you have a star that you know should be a point, and then you measure how the image of that star changes, and or in a more technical parlance you say you measure the wavefront of the light, then you can feed that information to your adaptive optics system, and then you can change the shape of your mirrors in such a way that you cancel out those deformations. And then in the end, you get an image of a quality that is almost the same quality of a spaced-based observation. So that's the cool thing about adaptive optics. So yes, these two stories were about testing and science verification. But then the last story that I want to tell you guys today about is about metallicity in spiral galaxies. So in astronomy, as you guys probably know, in astronomy we say that we have hydrogen, we have helium, those are the light elements, and then other stuff. And then everything that is not hydrogen or helium, we just call it metals, because we are astronomers and we like to call things in a way that doesn't make sense. But from a practical point of view, that's it. You have hydrogen, you have helium, and the rest of it you call metal. So even if from the chemical point of view those elements are not metals, you just call them metals. So almost excuse me, almost all the metals in the universe, they were produced in stars through nuclear fusion. And when stars die, then they release these metals into their surrounding environment. And these heavy elements, heavy metals, they are incorporated later into other generations of stars. And then eventually these stars explode, for example, as supernovae, and then release these more metals into the surroundings, and so on and so forth. So if we measure the abundance of metals in an interstellar medium of a galaxy, this is what astronomers refer to as the gas phase metallicity. You can study how a particular galaxy has evolved over time. You see how this abundance of metallicity changes with time. And by doing this, we have learned a lot of good things about galaxy evolution. So, for example, we know now that more massive galaxies, they have the tendency to be more metal rich. And this is probably because they have an easier time holding on to their metals compared to metals that compared to galaxies that have lower mass, for example, dwarf galaxies. Because these galaxies, they have masses that are so low that their metals are often expelled by strong winds produced by stars and other explosions from supernovae. So that's one thing that we have learned, that more massive galaxies tend to be more metal rich, but we have also learned that galaxies have on average moved from a lower to higher metallicity abundance over time, which is something that makes sense because if you think about it, then if you have more time for generations of stars to keep adding metals to a gas in a particular galaxy. So that's something else that we have learned. And at the same time, we have been able to measure how the metallicity abundance changes within a particular galaxy. We know that most galaxies are more metal rich near their core, near their centers, and more metal poor near their outskirts. This is something that might reflect, or that might tell us, that the galaxy formation tends to start from the inside and move outwards, so that there is more time for metals to build up in galaxy centers. So, but then in this story that I'm talking about, these are actually two papers published in the Astrophysical Journal, I believe. But they are available on the archive. And then the researchers of these two papers, of the authors of these two papers, they actually ask themselves another question, that is, can we be more specific about knowing the metallicity in galaxies? Instead of just considering how metallicities change as a function of radius, for example, can we start to consider how metallicities change around the disk of a particular galaxy? So this is the question that motivates the research that I'm presenting here. And here the researchers took an image, took a look at two different disk galaxies. These are the galaxies that you can see on your screen. They're just called, they're two spiral galaxies, NGC 1365 and NGC 2997. And the authors are trying to figure out if there are patterns in the metallicities, in the gas phase metallicities, that are related to the spiral patterns of on the galaxy's disk. So how do they do it? They take this phase on disks, these galaxies, and they take hundreds of optical spectra using a telescope in Las Campanas observatories. It's a 2.5 meter. It's called the DuPont telescope in Las Campanas Observatory in Chile, part of a program called the Typhoon program. And they actually integrate for a very, very long time, about 40 to 50 hours for each galaxy. It takes a long time, but then when you do that, you end up with a very high signal to noise data, and with very high resolution spectral maps of each galaxy. And then once you have all these spectral maps of the galaxy, then you proceed to measure the metallicity of the galaxies. And how they do it, the authors actually use a code to fit multiple templates, multiple spectral lines to a grid of models with different metallicities and other parameters. So we have talked about this technique in the past here in daily space. Then usually you have a theory and then you produce models. You have a model and you produce templates, and then you have your data, and then you try to cross-correlate those to the data and the models and try to see what matches best your data. This is basically doing a fit. And then in the end, it tells us these templates. They tells us about the metallicity of the galaxies, and then you end up with what they call metallicity maps in the regions of the galaxies, which is what you can observe right now in the screen for the two galaxies. In these figures that you can observe on your screen, the red colors indicate a more metal-rich region, and the blue colors indicate a lower metallicity regions. So obviously you can see a pattern, and it says you can see that it's a radial gradient in both of these galaxies. So metallicities are higher near the center of the galaxies, and they are lower near the outskirts. So we mentioned this before, and then we said that this is likely because the galaxy formation proceeds from the inside to the outskirts of the galaxies. But these actually are, well, all news, right? We already knew that. It is good that we found that and we found confirmation of that. But the researchers in these articles, they wanted to take our knowledge a little bit further, and then they wanted to know about this secondary metallicity patterns due to variations around the actual disk. So what the authors actually do, they subtract out that pattern that we saw in the previous image, that radial gradient, and then they look at the residuals, like what do we have after we take off what we already know. And that's this other map that we are seeing right now on the screen. It's very similar to the previous map, but it's actually showing us the residuals after we subtract that main radial pattern of metallicity. And at the same time, they also use another technique looking at lines called of hydrogen alpha or H alpha lines to identify the spiral galaxies, the spiral arms of each galaxy. And then you can see that as the dashed lines in these figures. And then then you can see that the metallicities in the spiral arms are higher than the metallicities outside of the spiral arms. So that's another pattern that they have been able to identify that you can just simply see by eyes by looking at these images. So how do the researchers interpret these results? So what does it all mean? So in one of the papers, the authors actually propose a physical model that could explain the patterns of the data that they gather. And one of the explanations that they put forth is they argue that the main process driving the gas phase metallicity within galaxies is something called self-enrichment. And this is a process in which you have massive stars that release heavy elements when they die, but these metals, they actually cannot travel far from when they were produced. So that is why it's called self-enrichment. So then, since new stars are more likely to form where the previous stars were, the same regions will slowly become enriched with heavy elements over and over again. They also mentioned that this is a process that continues for a region of gas that is flowing along the galaxy, around the disk of the galaxy. But then if you have this region of gas flowing around the disk of the galaxy, you have this process of self-enrichment, but actually this process stops or continues until the region hits a spiral arm. And they use an analogy. They say that the spiral arm acts like a traffic jam in a way that it compresses the region of gas that is moving along the disk. And then the arm stops the region of gas that is moving along the disk. And this is going to trigger a star formation and cause these clouds to collide. And then the gas starts mixing in a more efficient way. And then previously high metallicity regions, they get diluted downstream of the arm, and then they produce the observed metallicity pattern, where the spiral arms have higher metallicities than the interarm regions. And then finally, they have a companion paper and a second paper where the authors show that these metallicity variations, they're actually very hard to detect. And if you want to reproduce these results or continue these results, you need to have a really high resolution spectra and a high signal to noise measurement, which is what they actually had. That's why they had to integrate like for 50 hours or so, and they have to use a high quality instrument in order to get this data. So to better understand the metallicity patterns and the physical processes that drive this, we need deep high resolution spectra. So hopefully, yes, in the future we'll be able to get more data of this quality, and of course it would tell us about the history of the galaxy formation in the universe. So okay, that was all for today. So do you guys have any comments, any questions? And as usual, I ignore the chat up until this point, and then I go back and see if you guys have any comments or any questions. Let me see. Hello. Go tests. Yes. Yeah, we're very excited about tests. And adaptive optics was a beautiful invention. I agree. I think it's amazing how they just cancel out all the waveforms from the atmosphere. And one thing that I forgot to mention is that I said that you usually have your celestial target, galaxy or whatever, and then ideally, you should have a star next to the target in order to measure the distortion of the atmosphere, and then you can cancel them out. But usually, that's not the case. You're not that lucky enough to have a bright star next to the actual target that you are interested in. So, engineers and astronomers said, okay, let's create our own stars, and they actually shoot up to like lasers, and they act as artificial stars. So wherever you have an adaptive optic system, you usually have a bunch of lasers that act as your artificial stars, and then you can measure the wavefronts from those lasers, and then fit that into your loop and change the little shape of the mirrors and cancel out the waveforms of the atmospheric distortion and turbulence. Hello, Big J to that. Is adding adaptive optics expensive? I actually don't know. I would think it is, but I should know. But it's usually very high, like I don't want to say too complicated, but yeah, it's like a very delicate piece of equipment, and you need to actually have like these um, delicate mechanisms that change the shape of your mirror by microns, actually. So it's something that it requires a lot of precision, and hence I would think it's not an easy thing to add to your facility or to your local telescope. So yes, and usually in general, yeah, these things are very expensive. Only even the detector, like a CCD, is like of the order of tens of thousands of dollars. But a near infrared detector, which I was talking about also, the Hawk instrument, the near infrared detector is an order of magnitude more expensive than a CCD. Could be like a $500,000 or something like that. As one grows old, one gets stiffer like metals. Yes. Would a metal-rich galaxy have more planets? Yeah, that's a good question. I actually don't know, but maybe it's likely. And I'm thinking about the example, the standard example that we always go to when looking for exoplanets, which is the Earth. So we have a rocky planet, and again, I'm thinking also about habitable planets, because of course you can have planets with like giant gaseous planets like in our solar system or formed of whatever. But if you want to have a rocky planet here, then like the Earth, then most likely you will have to have several generations of stars that passed before the formation of that particular system, and therefore it would be reasonable to think that these are like a more metal-rich regions, no? As you have more generations of stars that have had time to produce these heavy elements. Um, define, okay. Um, okay, I'm looking at more questions. So the stars following the spirals, not just the density waves, like a slow traffic. Yes, I would think so, according to yes, so what we saw right here. There's another question that says, would any stars that pass through the arms have a signature of metals from the supernovas that are more likely in the arms? Mm, I actually don't know. that question, but the answer to that question. But I don't wonder what kind of signature usually. Yeah, you end up with signatures that are metal-rich regions, for example. But yeah, that's a good question, and I don't know exactly how to answer that one. Sorry for that. So the metallicity in the gas, not in the stars. Yes, here they're talking about the metallicity in the interstellar gas, or what they call the gas phase. So the heavier elements are produced by the stars themselves, by nuclear reaction themselves, and then one way of getting out is, for example, as some of them become supernovae and then they release the material. But the article was talking about the metallicity in the disk, in the gas phase, or in the interstellar gas in the galaxy. Then somebody says adaptive optics is probably less expensive than shooting an observatory with a 6.5 meter mirror to L2. Yes, that's one of the advantages, of course, of adaptive optics, that it might be expensive, but sending a telescope to space and operating it, and even if you send a telescope to one of the Lagrange points, which are very, very far away, which means that probably it's very hard to send someone or something, a robot, to fix it up if something goes wrong. So yeah, this is one of the motivations of investing in adaptive optics and these solutions that, of course, are going to be cheaper than operating something from space. We still want to send stuff to space because yeah, it's we do get way better resolution and we don't have the atmosphere, but of course, adaptive optics is a great way of mitigating those effects from the atmosphere. The Lagrange point is 4 times the way to the moon. Is that correct? Um, I think. I think it's about. I think the number I have in my mind is like 2 million kilometers from us, more or less. And I know that, but I might be wrong. So you guys can Google it right now. I could Google it. The moon, the average distance to the moon is between 300,000 and 400,000 kilometers. So order of magnitude, yes. Give or take, no, with astronomers, no, pi equals to 3, like in The Simpsons. So, yeah. Hurry up, James Webb, yeah. Carefully hurry up, yes. It's taking some time, but at the same time, it's gonna take the time it takes, and better to fix whatever you need to fix before you send it up to space. Yeah, Paranoid looked in Google it up for me. 1.5 million kilometers. Yeah, it's about 1 million miles away from the Earth. The second Lagrange point. All right. So I think thank you for your questions and for your comments. And yes, thank you so much for watching. This has been the Daily Space. It's a production of CosmoQuest, created by the Astronomical Society of the Pacific. And our goal is to put science in your brain. So if you like this show, please give us a follow. And if you want to sustain our efforts, please consider subscribing. And after this, next up on this channel, we will have Dr. Matthew Richardson and Joe. He bringing you Astro 101. So we're gonna see how Joe is, which is one of our programmers, is learning astronomy from Dr. Richardson. So that should be fun. And as usual, the Daily Space will be back tomorrow. I will be here, and it will be back tomorrow and every day of the week at 1 p.m. Eastern, the 10 a.m. Pacific, and 6 p.m. London. So see you tomorrow. Bye bye.